So we are going to check now what is the relation between the electric field and potential. Okay, as the next topic, relation between E and V. I'm just going to do some numericals on that. I'm not really going to, you know, uh, derive the relation. Okay, the relation between electric field and potential you can also guess. You can also check that the unit will be kind of easy to guess for both electric field and potential. Potential is volt, we know it. You can connect it with electric field as well. Okay, so whatever is the potential per unit charge will give you the more or less the electric field. Okay, so per unit distance, sorry, not the charge, per unit distance. So if I talk about electric field, what we have seen is E is equal to kq divided by r square, sorry. And if we talk about potential, it is kq divided by r. We can look and make a wild guess here. We can write down this E is equal to kq by r. Kq by r is there and one r is extra. So I can write it down as V divided by r. Okay. So the relation that we are actually looking for is this. Okay. This electric field relation with potential, okay, will be something like this. So we can write down this potential Vx, okay, or we can say the potential difference. Okay, we can obviously talk about potential difference here. As I told you, potential and potential difference are very closely related. Potential means you're taking a charge from infinity to a point, and difference means you're taking it from point A to point B. Okay, so that means if I want to find out the relation between potential difference and electric field, this electric field will be constant, imagining that it's a constant field dot the direction vector or distance vector. This is a dot product, so obviously this is going to be a scalar. So this is the relation that we should actually remember when we are talking about potential difference and electric field. Based on this, we can actually do a lot of numerical problems. We can actually derive this also, but let me not derive it right now. Let me just show you a numerical problem. Okay, and a numerical problem would be something like this. Okay, but before we proceed to this, we have to understand one concept very clearly. You see, if we take a positive charge on this side and a negative charge on this side, and let's not consider a charge, let's take a plate of charge. Let's say we have got these positive charges and these are all my negative charges. Okay, now we can actually give you the direction of the electric field. Okay, so you know sorry, the mic just got hit. Okay, anyway, so we have from this we can actually see what is the direction of the electric field. Okay, so if we have a positive charge and we put a positive charge somewhere, it will always get repelled. So that means it will always be away from the positive charge. So let's say these are my directions of the electric field. So this is my direction of the electric field. This is something which we already know. This is my direction of the electric field. And let's say we are measuring the distance. Let's say this is 1 meter, this is 2 meter, this is 3 meter, and so on. Okay, now if you look into the relation for potential, we see with distance the potential will decrease. Okay, so that means it simply says that if you look into the statement here, the potential will decrease. Okay, will decrease in the direction of the electric field, in the direction of E. So whichever direction the electric fields, the potential will also reduce. Okay, so you have to be very clear about that. We are going to use this logic to actually solve one numerical problem and try to understand it. Okay, let's try doing this one simple numerical problem. Okay, let's look here. So let's say I have been given, okay, I have been given a plate. Okay, let's say I have been given a plate and it has got a potential of, let's say, 20 volt. Okay, let's say this plate is A and then there is one more plate which is B. Okay, so this is my plate A and this is my plate B, and this is at a potential of plus 20 volt. Okay, this is plus, so obviously the direction of the field will be in this direction. Okay, this is my direction of the electric field. This is already given, this is an input to the question. Okay, and let's say that the distance between these two plates, you can consider it to be a parallel plate capacitor, is, let's say, 2 meter. That's given. Okay, you have to find out the potential at A is given. You have to find out what is the potential at B. You have to find out what is the potential at B. That's the question. Okay, so it's a simple question. You have one plate positive 20 volt. There is a plate B, and the distance between these two plates is 2 meter. You have to find out what is the potential at B, and VA is already being provided to you. VA is already being provided to you. Okay, now we will actually go by the definition of potential. Okay, so I'll use this formula. This is V, delta V, that means it's the potential difference, right? So if you look into the potential difference here, that means we are going to consider VB minus VA, okay, is equal to E dot delta R. Delta R is the distance, okay, and this delta R is nothing but given to be this. And let's say the electric field is also provided. You can check here also. You see the electric field, what will be the unit? If I just consider the magnitude, electric field is delta V by delta R. So that means the rate of change of potential with respect to distance, volt per meter. Let's say the electric field is given to be 10 volt per meter. That field is also provided. It has to be provided, otherwise you cannot find out what is VB. Okay, so that means VB minus VA, it can be written as E is 10 volt per meter into the distance, which is 2, which is 20, right? 20. So this is volt per meter, this is 2 meter, so that means this is 20 volt. So that is the potential difference. But question is not to find out the potential difference, you have to find out what is the potential at B. So VB can be written as 20 plus 20. Okay, so we can actually think about this in this way, or we can just let's not write down this. Let me tell you the simple concept. The potential difference is 20 volt. The potential difference is 20 volt. It says that VB minus VA is 20 volt. Okay, so the difference is 20 volt. That means VB can be either 40 volt, because if this is 40 volt, this would be 40 minus 20, which would be 20, or it can be 0 volt. It can be 0 volt. Both the cases are possible. Okay, this VB can be 0 volt, okay, or is VB can be 40 volt, because I'm saying that the potential difference is 20 volt. So it can be 40 or 0. Both the cases, the difference is 20 volt. The question is which one is correct. Okay. And for understanding this statement comes in very handy. The potential will decrease in the direction of E. So the potential was 20 volt. E is moving in this direction. So it should decrease. This is 40 volt. 40 volt is more than 20 volt. Okay. So it should decrease. 40 volt is less than 20 volt. That is increasing in the direction of the field. So that means this is not possible. Therefore, this potential at B must be equal to 0 volt. It's a very tricky question, since 0 volt is less than 20 volt. Okay, that's the main idea or concept behind this. Difficult to do. So I will give you one homework here, okay, and you have to use this concept that the potential will uh, decrease in the direction of the field. Okay, the question says that you are basically going to have, let's say you've got an electric field, a uniform electric field. Remember, uniform approach is different, non-uniform approach is different. We are saying uniform electric field, that means the lines that we have are more or less equally spaced. Okay, we have got an uniform electric field, and we have got a square in this case. Okay, let me say I have got a square in this case. Okay, and this square, what happens is, okay, I have this square, and let's say I'm having it as A B C D C D. Okay, and the electric field that we have in this square, or the electric field that we have here, is nothing but 20 volt per meter. Let's say 20 volt per meter. What's the question? The question is, you have to find out what is VB minus VA, what is VA minus VD, let's say. Okay, and then maybe you can try to find out what is VD minus VC, and then finally what is VC minus VA. You have to remember whether it is positive or negative, the potential difference. Okay, that's very important. And one more parameter I can provide it to you. Let's say that the distance between them is 1 meter. So this is 1 meter, this is 1 meter, this is 1 meter, this is also 1 meter. So it's a, so if we look into this question from our last class, we do understand that I have to find out what is the potential difference. So for potential difference, we are going to use this formula, delta V. Okay, so this is the logic here, that I will use this formula. Delta V is equal to E bar dot dr. Okay, dr is nothing but the direction vector, or whatever is the distance that we usually have in a direction. So if I take this, uh, I can take it as E or dr. Let's just take the magnitude cos of theta. So this is something which I already know. Now if you look here, that the electric field is moving in this direction, that means this is my positive side and this is my negative side. And in the previous class we have given a very important statement, that potential will decrease in the direction of the electric field, in the direction of electric field. So this is a very important statement in potential. So if you're talking about this and want to find out VB minus VA, that means this particular statement is this, VB minus VA. So first of all, we'll find out what is VB minus VA. So this is nothing but EDR cos theta. So you see the direction is in this direction. The directional vector is also in this direction, because I'm going from A to B, and of course the field is also in this direction, so it is making an angle of 0 degree. So that means if this is making an angle of 0 degree, I can simply write it down as E into dr, right? So this is the distance. So E is 20, already given, into 1. So that's 20 volt. Now this is the difference between VB minus VA. The question is whether this will be positive or negative. That's the most important part. So if you don't write down the sign correctly, your answer would be wrong. So you see VB is here, VA is here, VB is here, VA is here. The potential will decrease in the direction of the field. That means the potential at point B would be less than the potential at point A. So we are taking a smaller value minus a larger value. That means it has to be negative. That's why this is negative. Okay, so this is minus 20 volt. On the other hand, if I take VD minus VC, the potential will be more here, the potential will be less here. Same calculation goes in, angle is 0. This will come out to be 20 volt. Okay. On the other hand, we can look into VA minus VD, VA minus VD. Now you see this VA and this is VD. Of course, the distance is 1 meter, but it is making an angle of 90 degree. This is the direction of change, and this is the direction of the electric field. So they are making an angle of 90 degree. So I can simply write it down as EDR cos of 90 degree, which is 0. In other words, we can also say that this is actually equipotential surface. This is our equipotential surface. Why equipotential? Because the potential here or here are same. So it's a equipotential surface. I can take VC minus VA, so that means I can take this diagonal. This is there, this is 90 degree. If this is the diagonal, means this is 45 degree. If this is 45 degree, means this is also 45 degree. I'm talking about VA minus VC. That means I can simply write it down as E dr into cos of. Okay, now if you check the angle here, okay, this was 0 degree, this was 90 degree, this is 45 degree. And what will be my dr would be this and this square root. So I can simply write it down as E means 20 into dr would be nothing but 1 square plus 1 square into 1 45. Cos 45 is 1 by root 2. So this would be nothing but root 2 will get cancelled. I'll again get it here to be 20 volt. Okay, again positive or negative. We are saying VC minus VA. VC is small, VA is large. So this has to be minus of 20 volt. Okay, so that's how we can actually find out the the potential difference if you're basically having such problem. So now what we observed is that if we know the electric field, we can find out the potential. The question is the reverse possible? Okay, so can we find out the, so if we know the electric field, we can find out what is my potential. The question is, if I know, okay, let me just take it as delta, small distance, or the change in distance, you can say. If we know the electric field, we can find out the potential. Question is, if you know the potential, can we find out the electric field? As in this case, it's not as simple. If someone simply writes it like this, that yes, we can do it. We can say that E is equal to delta V by delta R. This is actually wrong. The reason is why it is wrong. The reason is it's a dot product with dot R. So it's a dot product. It's not simply a multiplication. It's a dot product. So we actually cannot write it like this. So what we have to do is we have to take the vector representation. If we are basically considering an electric field, in reality it is basically going to be a three-dimensional picture. So I can simply write it down as EXI cap plus EYJ cap plus EZK cap. Okay, we want to find out the potential using the electric field. Okay, and similarly, if I write down R bar, I can write it down as Xi cap plus Yj cap plus Zk cap. Okay, let's say that's my position. Okay, I can take R minus R naught. R naught might be origin, and I can take it X minus 0, Y minus 0, Z minus 0 will be, this will be the result. Okay, so what happens is, if I take potential now, V, it will be this dot product with this. So this I will give me Ex into X. This is into, this is not dot product, right? Plus Ey into Y plus Ez into Z. Okay, and this is my vector. Okay, sorry, potential. The potential will also have obviously it will have your three components. So this potential will have the components along X, Y, and Z. Now if I want to find out what is the electric field along the X direction, Y direction, and Z direction, I can easily do it now. Okay, so that means if I want to know what is my electric field along the X direction, I can write it down as the change in potential by the distance in the x direction. Similarly, I can take Ey is equal to delta V by delta Y, and Ez is equal to delta V by delta Z. So this is the exact scenario here. The electric field along the x direction, y direction, and the z direction, and we can now take the ratio, because remember R is a xi plus yj plus zk. So we have to keep that into consideration. So that's important, right? And that is why we have done it. Now if I just tell you that maybe your potential is given, the question is the potential would be given, you have to find out what is the electric field. Okay, so maybe your potential is given to be 2x minus 3y plus 4z. Okay, you have to find the electric field at 1 0 1. Suppose this is the question. So now you know that what is the x component of your potential, what is the y component of your potential, and what is the z component of the potential. And then you can find out the electric field x, y, and z, and then you can find out your answer for this. Okay, so these kind of questions where the potential is given and you're supposed to find out the electric field, you can use this and this formula and then actually find out the answer. Okay, so you can take this result and try to solve it. Okay, just a sec. Okay, yeah, let's continue. Okay, so we have to do this, right? So we can do it. So you can see this is del v by del x. So if you're looking into the differential part, we can simply write it down as del v by del x. I hope you get this, because if I take, this is r and we are having delta r. So if I write it down as delta r, this will be delta x, delta y, delta z, right? So I can also write it down here as delta x, delta y, delta z. So that's why it's delta v by delta x and so on. So this can be written as a very small change, del v by del y, and this can be written as del v by del z, right? So what we can do is we can actually use these results to find out the electric field. So if we want to find out the electric field is not a scalar, it's a vector. And how we write down the electric field, we can simply write it down as ex I cap plus ey j cap plus ez k cap. This is how we write down the electric field. Now I want to know what is the x component. So we already have the formula here. Ex is del v by del x. So if to check here, what is del v by del x? It's 2. Just 2. Right? Similarly, I can talk about ey, and this would be nothing but del v by del y. So it is minus 3. And let's just change it a bit. Let me write it down as 4z square, let's say. So that means del v by del z would be nothing but ez, and ez is equal to 4z, right? If you take del z of z square, it will be 2z, so it will be 8z. Okay, so I'll write it down as 8z. Okay, what is my thing? My aim is to find out this value, but at the points 1 0 1. So we can take it, ex is 2, there is nothing to change in x, so it will be 2 into I cap, plus ey is minus 3. So let me just write it down as minus 3 minus 3 j cap. For k cap we can do ez, and ez is nothing but 8z. So I can write it down 8 into, at what point I have to take 1 0 1. So z value is 1. So I can take 8 into 1 into k cap. So that means the electric field is 2 I cap minus 3 j cap plus 8 k cap. Okay. So that's how, if you know the potential, you can find out the electric field. Finding out the potential, knowing the electric field is easy, but from potential to electric field, we have to use this approach. So that is why it is important. Just a second. Okay, it's stuck, I guess. About spheres and so on, but we are not doing it right now. So the next topic that we actually want to do is equipotential surfaces. Equipotential surfaces. So I've already given you a basic overview of equipotential surface when we're discussing about dipole. In simple word, it means that the potential at every point on that surface will be equal. Okay, potential is equal on the surface. Potential. The question probably from this would be draw an equipotential surface for different kinds of system. So that may be a question will be equal on the surface. The properties of the equipotential surface is very important because from there the numerical might definitely be there. Okay, and equipotential surface mostly you have to imagine it in a 3D structure. Okay, so that means maybe you can actually consider a point charge. Let's take an example here. Let's take an example and let's consider a point charge. Consider a point charge. Now what happens is if you basically consider a point charge, maybe here we have Q. If you are drawing a sphere, all these points on the sphere, in here we can look into in the form of a circle, we can see it's a positive charge. At all points, the electric field will more or less remain the same. Remain the same, right? The potential will more or less remain the same because we know the potential formula is kq by r. So that means it is at equal distance and charge is there which is constant. K we know 1 by 4 pi epsilon naught. So whatever point you are getting in this circle, everywhere the potential is going to remain the same. That's the idea of equipotential surface. On the other hand, if we're talking about a surface which is at a larger distance, the potential will remain same here, and then you can keep on making these concentric circles. Okay, everywhere the potential will remain the same. Concentric means the center is the same and the circle is getting larger and larger, right? But we should also remember that this is basically a positive charge. That means the electric field is going away from it. So that means we know the statement that as we go from away towards the electric field, the potential will reduce. That means maybe it is 100 volt here, here it might be 80 volt, right? And here it might be 60 volt and so on. So this logic will never fail. This has to work. Then only we know that this is the equipotential surface that we have. Okay, so a very important statement. Okay, so basically for a point charge, okay, the question might be that draw the equipotential surface. You can simply write it down that the potential surface are the concentric rings, are the concentric rings. Now these equipotential surfaces that we are talking about actually has got some property, okay, that we need to know. Okay, but we can actually draw different kinds of equipotential surfaces as well. For example, let's say I will draw one cylinder, or maybe this is a line charge. Okay, I can have a line charge, positive or negative. If it's positive, it's going away. If it's negative, it is coming towards the field, right? And if I want to find out the equipotential surface, this is a three-dimensional picture. So what I can do is, for this kind of structure, if someone asks you to draw the equipotential surface, you can actually draw a cylinder. You can see that all the points in this cylinder is at equal distance from this charge. So this is one equipotential surface. I can draw one more equipotential surface here, and so on. Okay, so there will be a lot of equipotential surfaces for this. So this is equipotential surface, this is one more equipotential surface. So probable question from equipotential surface is to draw a equipotential surface, so that might definitely be asked. Okay, the next thing which is important in equipotential surface is properties. Properties of equipotential surface, that's very important. Okay, so we know the first property is quite obvious, that since the potential is same, okay, the potential is same. Okay, what we can say is that the potential difference, okay, if you want to actually know what is the potential difference, okay, this is a very simple question. if the concept is clear, you can definitely write it down. Between any 2 points, okay, so you can basically have an equipotential surface, something like this, something like this. This is my equipotential surface, potentially same here, maybe this is point A and this is point B. So it says that the potential difference between any 2 points, okay, on an equipotential surface is obviously zero, because whatever is the potential at A, same is the potential at B, so the potential difference will always be equal to zero. This also gives me another result as a consequence. We have told that what is the work done in bringing a charge from point, let's say, A to B, per unit test charge, is nothing but the definition of potential difference. So even if you consider this, if this is zero, the work done will also be zero. Okay, so that means that will bring us to the next statement. The statement will be no work is done. These properties are important. In fact, you can get numerical problem based on these properties. Okay, so we are doing a work on the system, so we can write down the no work is done by electric force in moving a charge. See, no work, become cross multiply, it will become zero, right? Moving a charge, equipotential surface. That's my second property. Okay, so you can obviously see it from this particular result, so anyway I'm not doing it. Okay, there can be other properties as well. We can always talk about the direction of the electric field in an equipotential surface. So always see this. If this is my equipotential surface, the direction of the electric field will always be perpendicular to the equipotential surface. Okay. This example we have already seen once. I will try to repeat that thing. So the direction, this is the third property, which is again important. Electric field is always perpendicular to equipotential surface. This is always perpendicular to the equipotential surface. Okay, you can think it in this way also. If we basically talk about dv, we already seen that is equal to nothing but E dot dr. Okay, and we are saying that it's an equipotential surface, so if we talk about the difference here, dv will always be equal to 0. Okay, there is no change in potential. E dot dr means I can simply write it down as E dr cos of theta, right? Now, if there is an electric field, E cannot be zero. We can obviously consider E to be zero. Then we then simply say that the electric field does not exist. But let's say the electric field is existing, the distance would be there. The only thing that can make it zero is cos theta. Okay, so that means cos theta has to be zero. It simply means that theta has to be 90 degree, because cos 90 is zero. So it simply says that the angle between, okay, the electric field and dr is equal to 90 degree, right? So this is my dr, because I'm going from A to B, so this is the direction. The electric field has to be perpendicular, otherwise you're never going to get it to be zero. Okay, so that's a very important thing. Okay, so whatever we are talking about here, the field lines, okay, the electric field means we're talking about the field lines that is always perpendicular to the equipotential surface. Okay, so that's very important. So if you recall, uh, when we talked about dipole, okay, when we were talking about dipole, and we said that there was a charge here plus q, and there is a charge here minus q, and if you're basically considering a plane surface here at all the points, it is an equal distance from plus q and minus q. That means the potential will cancel out each other and I'll get zero potential. So this is an example of equipotential surface. But we can actually talk about different problems. There might be questions where they will ask you draw equipotential surface. They will give you a system and then they will tell you to draw the equipotential surface. Okay, so maybe I can take one example. Let's say we are having an electric field like this. Okay, this is my electric field and this is provided to you. Okay, this is a parallel plate field. Okay, a line field, and this is the electric field. You have to draw the equipotential surface for this particular system. Okay, so what we can do is we can simply write draw like this is actually a plane that we are actually drawing. Just imagine it in 3D. My drawing might not be that well, but you look into these so these are the planes that we have. Okay, these are the planes. Let me use a different color maybe. These are the planes that we have. So you consider any point on this plane, the electric field is in this direction and the change will be in this direction, always making an angle 90 degree. So the potential everywhere on this particular plane is going to be zero. So you have to just check for this result. That is important. Then only you can say that the electric potential surface will be equipotential. You have to always check delta V is equal to E T R cos 90. It has to be like this. This has to be 90 degree between E and dr. If that's the case at every point, that means it's an equipotential surface. That's how you can actually draw it. So if you look here, see this is delta V. 90 would be nothing but you're moving from here to here, but the field is in this direction, so it is 90. Obviously it's a equipotential surface, but the potential will reduce towards the field, change in field. So if this is let's say 20 volt, this has to be less than 20 volt, so maybe it will be 10 volt or something like that. Okay, so these concept has to be clear, very important. Okay, okay. There is one more property that we should actually note down. Okay, let's write down that the fourth property. The fourth property is no two equipotential surface should intersect each other. That's very important. Should intersect. Two equipotential surfaces cannot intersect each other. Now we know that the direction between the electric field and the vector is 90 degree in an equipotential surface. So let's draw one equipotential surface. Let's say this is one equipotential surface. Okay, and let's draw another equipotential surface which is intersecting with this. Okay, to prove it, let's imagine that this is interacting with this equipotential surface. Okay, so for this particular plane, the surface is in this direction. That means the electric field has to be in this direction. Okay, if we consider this point, let's say this point, electric field is in this direction. But if you are considering the horizontal plate, horizontal region, we know this is the surface, so that means the field has to be in this direction. So we can see that at the same point the electric field is in two different direction, which is impossible, right? For a particular system it has to be in one particular direction, and that's the proof, or we can say the indirect proof to say that no two equipotential surface can intersect. Okay, they can intersect. Okay, so from here we can conclude uh, E cannot be in two directions at the same point. So this indirectly tells me that why two surfaces cannot intersect. Two equipotential surfaces can never interact. So these are the four important properties that you should remember. First, the potential difference will obviously be zero between any 2 points on an equipotential surface. And if you look into the formula, use the formula, we know that the work done will also be zero. Okay, the direction of the electric field is always perpendicular to the equipotential surface, and no two equipotential surface will intersect with each other. We have also proved them in short. Okay, now let's just one question that comes to my mind is, let's take one example to sketch a equipotential surface. Let's consider our dipole, and we want to actually sketch the exact equipotential surface for that particular dipole. Okay, if you want to check all the points at which there won't be any uh, uh, potential difference. Okay, so if I look here, this is only one plane that I have drawn. Okay, so maybe we can draw it even more clearer. I can take this is plus q, and this is minus q. Okay, so if I actually want to draw what is the field line here, the field lines will always go from positive to negative. Again, this positive to negative, positive to negative, positive to negative. So that's how the field lines will actually move. Okay, and then again it will be positive to negative. It's coming in, it's going out. It will always go out of the positive lines. This will go out, this will go in, right, and so on. So I can draw more lines like this. Now we have to find out what is the equipotential surface. If we are actually able to draw the lines of force, we should also be able to draw the equipotential surface. As we said, at every point it should make an angle of 90 degree with the direction of the field. So at this particular point, all these lines are lying in the same plane. Okay, so this can be written, this can be drawn like this. So this is the plane that we actually have. Okay, so this is the plane that we actually have. Okay, so this is my plane. On the other hand, if I talk about this particular point, there is a curvature which is coming. So that means it will be 90 degree here. For this it might be slightly here, it will be here, it will be here. So it's not going to be a straight line anymore. It will be something like this. It will be something like this. And as we come closer to the charge, it will form concentric rings. It will form concentric rings kind of structure. These cannot cross each other. So when you draw it, you have to be very careful. It will be like this, closer to this. And then if you just check for the 90 degree angle, so this is how the equipotential surface, the entire equipotential surface will look